Okay, so new definition. Let A and B be n by n matrices. Then A is similar to B if there exists an invertible n by n matrix P such that B is equal to the product P inverse times A times P, or equivalently, A is equal to the product P times B times P inverse. If A is similar to B, this is denoted this way. A is similar to B. So notice that if A is similar to B, then B is similar to A. So we simply say that A and B are similar. So let's prove a theorem. Let A and B be similar matrices. Then the determinant of A is equal to the determinant of B, and A and B have the same characteristic polynomial, and thus the same eigenvalues. So proof. First statement. Suppose that A is similar to B, then there exists an invertible matrix P such that B is equal to P inverse times A times P, and so the determinant of B is equal to the determinant of the product P inverse times A times P, and the determinant of a product is the product of the determinants, and so we have the determinant of P inverse times the determinant of A times the determinant of P. Now these are simply real numbers, and so we can rearrange them so that we have the determinant of P inverse times the determinant of P times the determinant of A. And we can choose to regroup these two products so that we have the determinant of P inverse times P times the determinant of A. P inverse times P is the identity matrix, and so we have the determinant of the identity matrix times the determinant of A. The determinant of the identity matrix is 1, and so we have 1 times the determinant of A, or simply the determinant of A. So if A and B are similar, then they have the same determinant. So second statement, since B is equal to P inverse times A times P, we have that B minus lambda I is equal to P inverse times A times P minus lambda I. Now we can replace the identity matrix with the product P inverse times P. And so we have P inverse times A times P minus lambda times P inverse times P. So notice that in both of these terms, we have post multiplied by P. And so this is the product of the quantity P inverse times A minus lambda times P inverse, all times P. Now we can replace the term lambda times P inverse by P inverse times lambda I. And so we have P inverse times A minus P inverse times lambda I, all times P. And so now in these two terms, we have pre-multiplied by P inverse. And so we can factor that out so that we have P inverse times the quantity A minus lambda I, and that quantity times P. And so the determinant of B minus lambda I is the determinant of the product P inverse times A minus lambda I times P. Again, the determinant of a product is the product of the determinants, and so we have the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. Again, these are real numbers, and so we can regroup them to have the determinant of P inverse times the determinant of P times the determinant of A minus lambda I. So we have the determinant of the product P inverse times P times the determinant of A minus lambda I. P inverse times P is the identity. So we have the determinant of the identity times the determinant of A minus lambda I. The determinant of the identity is 1. So we have 1 times the determinant of A minus lambda I, or simply the determinant of A minus lambda I. And so if A and B are similar, then they have the same characteristic polynomial and therefore the same eigenvalues. Okay, new definition. A diagonal matrix is an n by n matrix with all zeros, both above and below, the main diagonal. In other words, the only non-zero elements in a diagonal matrix occur on the main diagonal. So notice that a diagonal matrix is a special type of triangular matrix. And so the eigenvalues of a diagonal matrix are simply the elements on the main diagonal. So new definition, an n by n matrix, A, is diagonalizable if the matrix A is similar to a diagonal matrix, which we'll call D. In other words, there exists an invertible matrix P such that D is equal to the product P inverse times A times P. All right, so now let's begin to bring these concepts from linear algebra back into geometry. So consider the general equation for a conic, which was or is ax squared plus b times x times y plus c times y squared plus f times x plus g times y plus the constant h is equal to 0. We will call this equation star. So let the matrix A be the 2 by 2 matrix with first row A be divided by 2, second row be divided by 2c, and so the coefficients in these first three terms occur in this matrix. J is the column vector with the coefficients f and g, and x is the column vector of the variables x and y. Then x transpose times A times x is the row vector xy times the matrix A b divided by 2, b divided by 2c times the column vector xy. So we'll multiply left to right, and so we'll do the product of the row vector xy with the matrix. A row vector times a matrix will give us a row vector, and the first component is ax plus b divided by 2y. And the second component is b divided by 2x plus cy. And we'll multiply that row vector with a column vector xy. A row vector times a column vector is a scalar, that is just a real number. And that'll give us ax squared plus b divided by 2 y times x plus b divided by 2 times x times y plus cy squared. Now, since y times x is the same as x times y, we can rewrite this as ax squared plus b times x times y plus cy squared. Now, remember the column vector j is the column vector of the coefficients f and g. And so j transpose times the vector x is the row vector fg times the column vector xy. Again, a row vector times a column vector is a scalar, which is fx plus gy. And so the general equation for a conic, the equation star, has a matrix form x transpose times A times x plus j transpose times x plus the constant h is equal to 0. Now this first term is an example of a quadratic form, but before I can formally define a quadratic form, we need some preliminary definitions. So new definition, a homogeneous or homogeneous polynomial is a multivariate polynomial that is a polynomial with more than one variable, where each monomial has the same total degree. Which is the sum of the exponents of the variables. So, for example, the polynomial x cubed plus 2 times x squared times y plus 3 times x times y squared plus y cubed is a homogeneous polynomial of degree 3. Each of the monomials has a total degree of 3. X squared times y, where the exponents are 2 and 1, has total degree of 3. X times y squared, where the exponents are 1 and 2, again, it has a total degree of 3. And of course, the cube terms have a degree of 3. All right, so now we can define a quadratic form. Nope, one more definition. A symmetric matrix is an n by n matrix, which we'll call A, such that A is equal to its transpose. So if a matrix is equal to its transpose, then that means that the elements A sub ij are equal to the elements A sub ji. So now we can define a quadratic form. A quadratic form is a homogeneous polynomial of degree 2 and it is typically represented in matrix form. Q of the vector x is x transpose times a matrix A times the vector x, where A is the symmetric matrix of the coefficients of the polynomial, and the vector x is the column vector of variables. So in the quadratic form, the diagonal elements that is the elements A sub I are the coefficients of the square terms x sub I squared, and the off diagonal elements a sub ij, where I is not equal to j, are the half coefficients of the variables x sub I times x sub j, which is equal to x sub j times x sub I.